Perfecto.
So, good morning. My name is Iñaki, and today we're going to present the problem situation, the design of an agricultural irrigation system. And we are.
We are Bernardo Sari Lopez.
Oh, Iñaki habla de ciencia.
Juan Germán Castillo Ortiz.
Víctor Fernando Santalaya.
Héctor Rodolfo Serafino Alberto Ortiz.
Axel Alejandro Pasana Castellano.
And, well, to introduce this topic, first of all, we purpose designing a passive irrigation system using a Maria Palo for agricultural communities without electricity, leveraging experimental statistical principles along with other creativity to optimize water use and enhance sustainability.
Okay, here we have first the design of the Maria Palo. We did it like this because we wanted to have a certain height between the excess tube and the tube that had the contact with the air. And the height that we used that was 19.5 centimeters, and this height was variable dependable on the type of experiment that we did. But in this case, the final product has 2.5 centimeters. Here we can see the heights that we used previously in the different experiments that were 2 centimeters, 4.5, 7, and 10 centimeters.
During the experiments, we used tracker to measure all of the levels in different moments in time. We divided the videos into 20 different frames where we checked the water level, and we made an equation in respect of time and position to get the velocity of the water. Here we have the equation of the velocity of the tank, where hi is the water level at height and time ti, and hi minus 1 is the height at the previous time ti minus 1. Here we have the results in Excel, where we were able to get the equation of velocity, its uncertainty, of the measurements that we initially did, and we also get all the times, the position, and finally the velocities of each one.
Alright, so now let's get into the height versus time graphs. So first we have our first try, which had a slope of minus 0.097, and with the second test, which is below over here, we have a slope of minus 0.0015x. In our third test, we did it again, and we have a slope of minus 0.0017, and in the fourth test, minus 0.002. So, which means this slopes, well, it's the exit velocity of the tank. It's basically the slope that we talk about on each of the straight lines.
These are experimental velocities.
Okay, with those experiments made, we finally decided to make a space where we could minimize, where we can simulate how the irrigating system would work. So we use this. This one is the design that we use for the base for the Mariel bottle to put it at a certain height, and these are the ones that are covering it. And it was the first design that we took to make the real design. And finally, this is what we created with the objective of seeing the flow of the water in each one. First, it goes through the first tube, and then it divides into two, and those two get divided into two to give the flow rate to each of the tubes that are going to give the water to the plants.
Then we have the different steps of the creation of the experiment. First of all, we had to do a planification. First, we had to do some drawings and really plan out which were the steps to do to create the experiment. Then we get the results and also the experimentation, trying different versions and different measurements to see what would happen with the different certain types of variables. And of course, then the construction of each one of these pieces. We have to construct each one and put them together. So at the end, we have to put everything to see this experiment of the Marriott bottle work. And of course, at the end, we have the prototype, which we have the Marriott bottle and the different types of plant to put the water in and to see how the velocity of the water comes out through. And of course, we have the Bernoulli equation, which we use the pressure, the density, and the velocity to see how the water comes out to the plants. Here, instead of using, for example, some type of electricity system or some type of technological advancement, we can use the physics to know how to use the velocity to be constant and really be in the water to use it for agricultural and other purposes.
Well, now applied in the irrigation system, the theoretical exit velocity is calculated of the, well, applying the square root, 2 times multiplying the gravity times the height of the Marriott bottle of the water. This height is the separation between the two tubes, the vertical tube and the drain tube. And we obtain that value of exit velocity, that is 0.62 meters per second. And this is compared with other heights. Now we apply the continuity equation. We know that the flow rates are defined as the area times the velocity. In this case, the first tube that comes from the Marriott bottle is divided into two first. This means that we have two flow rates, that is number 2 and number 3. But these are identical. Why? Because the area is the same. We calculate the cross-sectional area in that way, and it was of 0.00005027 meters. And this one, we use it in this equation. But as they are identical, we can say that this area times velocity is the same, so we multiply them too, as it's the same.
Yes, okay.
Then, for obtaining the next velocity, we simply divide the initial velocity between 2. And the result was 0.3 meters per second. And we also calculate the total flow rate, multiplying the area times initial velocity. And as it also split, it divides into 2. And the result is 15.74 milliliters per second.
Yeah.
Continuing, then after the first split, it's again split and into 4 different tubes. So now we can divide the initial velocity into 4, and the result is 0.157 meters per second. And also the flow rate is equally divided between 4, and the result is 7.87 milliliters per second.
Okay.
And now we're going to talk about the drippers, that are the holes where the water exits. There are 3 drippers in each line. So, and each one has a 1 millimeter diameter hole where the water exits. So we can now calculate again the area, because this time is different because the hole is more little. And we calculate the area, that is this one, and we use it now in the calculation of the flow rate. This is the previous from the well, this is the area. This is the area, and we divide it into 3 to calculate the flow. And the flow per dripper is 2.62 milliliters per second. And here, this formula is deduced by the continuity equation, that is now that the flow rate of the dripper divided into the area, cross-sectional area of the dripper, it's going to be the velocity, the exit velocity of the water. And it's going to be 3.34 meters per second. And these are the final results.
Well, finally, we conclude that this system it's a very viable option in some rural places, which the access of electricity is very difficult, and also in those places that suffer of very frequent natural disasters, because this prototype maximize the efficiency of the water, and also the distribution back because of the height of the bottle of Marriott, as we saw in those brief in the previous slides. we can still see that the height of 10 centimeters is the base for a very efficient dispersion along all the system.
And well, we can see that
Here's
there is
a video of the
irrigation system works.
Do you want to see how it works?
Yeah, we can show you how it works.
Yeah.
Out there.
Right, so the ball.
Last. No, no.
El video,
¿Quiere ver?
puedo ver que, bueno, como
¿Quiere
gusta,
verlo?
como
¿Quiere verlo?
Ahí está el video, pero
Sí, acá está en video,
Aquí está en el
pero
video.
lo podemos
no se
ver
puede
acá.
caer el agua.
aquí para que
Sí, bueno, pues ya con el video vimos que funciona. Bueno, les tengo que hacer una pregunta. ¿En qué influye
voy a ponerle pausa al video.
desde aquí hasta donde sale el agua?